Hey, what's up, guys? Yeah, so today, this is my own lecture about the introduction to topology, and I will basically start from metric space and go to open set, closed set. Basically, some of them overlap with the, I think, the advanced calculus, and I will go to T1, T2, T3, T4, and T half and Hausdorff space, and then try to collect everything in the like covering space, the homology, that cohomology of fundamental group, and also some servers. Yeah, so this is what I want to make my own introduction on topology video. So I will start from basic and try to go. Okay, and I hope you guys subscribe to my channel. Okay, and I mean there's a many topology lecture note, so you can just go to check online. Okay, and but I make my own notes. Okay, so the first one that today, let's quickly review the metric space. Okay, so let's say we get a set which is non-empty, and you get set x to x, which is view as a distance. Okay, and satisfy. So satisfy the first one is that the dxy greater than 0 or xy belongs to x. Basically, it's the distance. And the second one is that distance should be symmetric. And the third one should be if the distance is 0, if and only if x equals to y. And the fourth one is that there's a triangular inequality. So x z is equal to dxy dy. Okay, so this is a metric space. And the standard example would be let's say you take the x to be the Rn, which is n-dimensional Euclidean space. And the distance, you can define distance to be or basically you can define distance to be so-called P naught. Okay, so which is each called xy minus I to the P, from 1 to n. Okay, and there's also the so-called infinite norm. So basically, there's a thing called infinite norms. So infinite norm means that you can define dxy to be the maximum of the y. And a very simple exercise to prove that there are all a metric space. Okay, and there is also a discrete another example, which is a discrete metric space. So let's say you take x to be some non-empty subset, and then you can define a distance xy to be 1 if x equals 0, if x equals y, if x is not the same as y is defined as 1. Okay. Okay. Okay, so now let's quickly review. So now, so first, let's define open sets in matrix. Okay, so the good thing is that I guess everyone knows about calculus, right, or advanced analysis. So you know that you can define a radius. You can define a ball, right? So we can define a ball, which is usually identical to Brx, which is all the points belongs to x, such that the distance between yx. Okay, so sometimes I will use the absolute value notation, although it's not absolute value that you understand. So y minus x is less than r. Okay. So this is the so-called open ball. Okay, and usually I will define a closed ball if there's an equal sign. Okay. And so one can define a subset O of x is open if every point, every x belongs to O, there's there's a radius r of x, such that Brxx, which is open ball, which is open. Okay, so this is the open set. Means that let's say for each point x, there's a small neighborhood, open neighborhood, such that this x belongs to this whole ball belongs to this space. Okay, so this is standard open set. Hopefully, this is not the first time you have seen it. Okay. Okay, and also the theorem that I think I already proved it. I think I proved in my advanced calculus video. So I will post link below if you're interested. So basically, this is common that you can check that. So first one is you can check the empty and the whole space x is open. Okay, so So this is trivial. You can check for X is open, right? X is open is trivial. And the second one is that any the countable collection, let's say AI of all is open if all AI is open. Okay, you can check by this is also easily checked by axiom, because if you take, let's say you take X belongs to the union of AI, means that X belongs to sum of AI, right? So that means you can take the open ball, right? So you can easily prove that you can take Ri X belongs to the subset of AI, which means that the Ri of X is basically the subset of or whole. Okay, so we can prove. Okay, and the count of the finite intersection of AI is also open if every AI is open. So if every AI is open, then the finite intersection is open. But this is also proved trivially because it's finite. So you can take the for each rate for each X, for each I, that you get some Ri, which is that open ball for X, and the user will take the minimum. Okay, so closed set. Okay, so closed set is also trivial, right? So in order to say closed set, I think we need to use we need to write down a definition. So let's quickly do it. So I can define a closed set A if A complement is open. Okay, so this is like a quick way that you can quickly prove. Okay, and another definition is that A is closed if A contains its limit point. This will be a little bit tricky because I need to define limit point. Okay, so let me just quickly define it. So if Z is a limit point of A, is a limit point of A, means that what? Means that every open set cover X, covering Z, intersects A. So I should say that, okay, so Z is a limit point of A, means that let's say Z, right? This is A. Okay, so that means for each open neighborhood, right? For each open neighborhood, there's intersection points contains some there's every open neighborhood of Z intersect with a non-trivial. So non-trivial means that non-trivial. So non-trivial means that the intersection contains more than A. Okay, so contains more than Z. So this means that however open ball you choose, you can always find a point Z prime such that the Z prime belongs to A. Right, so Z is infinite close to A. Okay. So I think one example, maybe let's say you take A to be 0, 1, right? And let's say in a real line, so 1 is a limit. Okay, because you can check that this is 1, right? And however small open neighborhood, however open ball you choose, you will always find a point here such that this guy right intersect with A. Okay, so I think we already discussed the metric space, and let me just quickly give you a definition of the general topological space. And once we define it, then we can start doing about definition other things in the next Okay, so definition. So this is called a topological space. A G-code space X. Okay, so when somebody say topological space X, you're saying that X tau. Okay, so X is a set, X is non-empty set, usually is not empty, and the tau is a collection of, so tau is a subset of P of X. So this means the power set of X. Okay. And so the collection of tau, so tau is called tau is the collection of open set. Okay, so this means that for every tau I say is open. Okay, I define every guy in tau is open. This is my definition. So every guy in tau is open, and every open set in R are exactly tau. So tau is all open set. Okay, but I should have some axiom to say that what is the relation. Okay. So satisfied. Okay, the first one is that phi must be tau, right? So empty and x, right, must be tau. And the second is that the finite the countable union of element in tau must be in tau. So connection, I should say a countable union of element in tau must in tau. So this is like the imitation of original open set as an open ball. Okay. So the third one should be what? Finite intersection of element in tau must in tau. Finite intersection. Tau. So this is the general topology, and you can obviously that so one could easily see that we just proved that the matrix space with open ball, that open ball, okay, open ball is or open set, which every point has some open ball, is a topological space. Okay, so one can check, maybe that's to some stupid example. Let's say we can consider x in the 3 points ABC, and you can check that. You can easily check. This is very good exercise, and you can check phi and x, and where A and B is a topology or not. Right? So obviously, this guy intersection is trivial, right? But their union A B should. So this is guys not topology. Because you should be able to collect this. Right? So this is not topology. Okay, and then you can check. Yeah. Okay. So this is the topological space. Okay. So let me just introduce so-called induced topology. So induced topology is let's say you take the subset of X. Okay. And you can, and then you get some tau, right? It's called tau of X. Right? So X is let's start from some topological space X and tau of X, and I want to define tau Y. Okay. So let's say I take the subset of X, and I can define tau Y to be the intersection of tau X with Y. Okay, so tau Y means that every element, let's say O intersection with Y, where O belongs to tau. Okay, so this is called the induced topology. Okay, so basically for every subset, you can build a topology. So this is how do you define? So how do you define a sphere, right? How do you define a subset? The one topology of sphere. So idea is that you put sphere right into the 3-dimensional, and you use an induced topology. So in R3 there is a standard topology. Right, so in R3 there is a standard topology. Let's say this guy is open, right? But you can do the intersection with the sphere, right? So you can see that in a sphere that this open, this guy open. Right? So this is the induced topology. So I think when people say the topology of the sphere, that they are saying that they're doing the induced topology. Okay, I think up to now is okay for today. And next time we say some closed set and continuity, and talking about the homeomorphism. Okay, so see you guys in the next video.